Hi, thank you for attending my talk at the PIRE 2020 virtual workshop on polymer-derived ceramic fibers. My name is Spencer Dansereau. I'm a PhD student at the University of Colorado Boulder, and this talk will be on polymer-derived silicon carbide micro-composite fabrication via nano-layer infiltrations. The principal investigators on this project were Dr. David Marshall and Dr. Rishi Raj, and was done in collaboration with Ali Bedran and Ben Robles. There were two departments that were involved in this project at the University of Colorado Boulder, the Aerospace Engineering Sciences Department and the Mechanical Engineering Department. It is important to give a quick overview of both what a ceramic matrix composite is and what a polymer-derived ceramics are. CMCs, or ceramic matrix composites, are a class of fiber-reinforced composites that have favorable mechanical and thermal properties, especially for high-temperature aerospace and energy production applications. Polymer-derived ceramics are a class of polymers that, when heated, go through pyrolysis and are reduced down into a ceramic residue, such as silicon carbide. This work looks to merge these two technologies by creating a ceramic matrix composite via a novel method of using PDCs. So where are CMCs currently? There's a couple different applications for ceramic matrix composites. Most notably, hypersonics. They're used in both leading-edge applications as well as the propulsion systems, as they experience very high heat flux during flight operations. A second notable application in the aerospace industry is in gas turbine engines. In gas turbine engines, the hot section components experience very high temperatures, and to further increase the thermodynamic efficiency of next generation engines, an even higher temperature is required. In order to reach these higher operating temperatures, which in turn increase efficiency, a new material is needed, a ceramic matrix composite. Another use of ceramic matrix composites is in energy production, such as nuclear fusion or nuclear fission. A broad overview of the entire project that I am working on. This presentation will focus just on the first bullet point. However, it is important to understand where this sits in the scope of the whole project. The first point, which is the topic of this presentation, is on developing a nanoscale control additive manufacturing process to create the matrix via polymer-derived ceramics around silicon carbide fibers to create that CMC we're looking for. Next up is also using this same novel robotic system to create the matrix in these CMCs, and using that to create ultra-high temperature ceramic thermal barrier coatings. And then we'll move on to characterizing material fabrication parameters so that we can reach a microscale controlled porosity, thus permeability in these composites, which can be used for active cooling applications such as leading edges and hypersonics. The next step from there would be looking at and characterizing just how effective these newly fabricated CMCs and the respective active cooling aspects of these CMCs are when exposed to supersonic air plasma flows. Now, focusing on the first bullet point, breaking down into three objectives for looking at the buildup via PDCs of this matrix for the CMC. We're looking at optimizing the robotic system deposition parameters to look for uniform adhesion, but without any cracking or bubbling in the matrix, very important. We're also going to be looking at matrix infiltration parameters. We looked at matrix infiltration parameters of polymer concentration, polymer type, as well as the type of solvent, and whether or not silicon carbide microparticles should be added to control the porosity and thus permeability of the CMC. And then using the same automated system, the silicon carbide precursor is proposed to be doped with either diboride particles or, more notably, the hafnium butoxide addition to increase the thermal resistance of these CMCs, and thus increasing the operating temperature at which they can survive and fully operate. Now, I mentioned this automated system that using for this project. Here is a basic schematic of how this system operates. It's enclosed entirely in an argon glove box that's positively pressured, and there's 4 different stages. The first stage is the material matrix bath, or smart syringe deposition, which deposits a diluted polymer precursor onto the sample, which is either a woven lattice of fibers or a single fiber tow. That is then moved on these 2-dimensional robotic tracks in 2 axes. First into the 350 C furnace. This is the cross-linking furnace. From the cross-linking furnace, we then move into the 900 C furnace. This is the pyrolysis furnace, and then we move into the cooling chamber. It's very important to have this cooling chamber, for if we do not have it, the precursor is too hot, so that when the polymer is redeposited onto the structure that we're looking to fill up, it doesn't wet out enough and you actually get bubbles. I will show an image of this later on. You can see what happens if the sample is too hot when you try to re-infiltrate the polymer into the matrix. Moving on, here's just a SolidWorks model of how the system is currently designed and how it actually physically looks currently. And then a few pointers on this matrix buildup. We're looking at building up material in between the fibers by layer. So each layer deposits a very thin, within the sub-micron range of ceramic residue, and then we're building it up layer by layer so that we don't end up with a lot of cracking in the matrix due to the shrinkage of the ceramic as it undergoes pyrolysis. Thus, the repeated coatings are the best way to avoid voids or cracks within the matrix due to that shrinkage. Some previous work that I did earlier on in this project is working with carbon fibers and then Cereset as the infiltration agent, Cereset PSC20. As you can see, the controlled carbon fibers and then the 30 cycles at 1% Cereset infiltration. There's 2 reasons we moved from Cereset to the SMP10, as you can see on the bottom half of this SiC-SiC composite fabrication slide. The Starfire SMP10 reduces down into a almost pure silicon carbide residue, which is what we're looking for. We're looking to create here a silicon carbide ceramic matrix composite. The other reason we moved away from Cereset is because it's no longer commercially available. For this research, the fiber preforms were done using the high nickel-on fibers. Most notably here on this table, the average filament or fiber diameter is 14 microns. Moving on to the first of the SEM images, this is an image of the raw control fibers. This fiber in the image does not have the factory coating burned off of it. This is just right off of the factory tow, which is it's a useful starting point to compare to. And then after 300 seconds of a primary burn off, this is an image of 5 cycles in. In a few slides, we're going to do a comparison of the diameters between initial fibers, which again to the fact sheet has an average diameter of 14. These fibers, as you'll see, have an average diameter of 16.5 microns after 5 infiltration cycles. All the subsequent images, as well as this image, have 1% the SMP polymer per mass diluted with hexane, and then the optimization at this point for the automation system in the robotics is to have 25 seconds in the cross-linking furnace, 50 seconds in the pyrolysis furnace, and then 30 seconds in the cooling stage. Moving on from 5 cycles, we can see 10 cycles. Here we can see a more significant buildup of interstitial matrix between fibers. We do have cracking. As you can see, a large crack coming down the middle. This isn't a major issue at this point because many of the cracks, as they form initially in the cycles, they are actually re-infiltrated by subsequent infiltrations, and they actually get filled up. So even if you have a large crack, this crack is about 1.4 microns in diameter, in width. This actually will be re-infiltrated. The polymer will seep into this as it is re-infiltrated and fill up the crack as it builds everywhere else as well. So this was 10 cycles, again with the 1% SMP10 and the same robotic system parameter. Here we can see 15 cycles. There's quite a bit more interstitial matrix buildup. However, the matrix buildup is not delaminating from the fibers and is building up a fairly good matrix in between these fibers. I will talk about the almost fuzz looking on the right hand side of the fibers in a moment. Here we're looking at 30 cycles. This image has the 300 seconds of primary burn-off, which the previous slide did not. Again, I'll get to that in a second. But this one, as you can see, it's a really significant matrix buildup. Again, that has good adhesion without any cracking or bubbling. You can see a few small cracks, but again, those can get filled in by subsequent infiltrations. And then we're going to move on. This is a good result. It's really solidifying a pretty significant matrix here. And then again, as I mentioned, we're going to compare the diameter so we can get an initial thought as to what the average deposition per cycle is on this. Here, this is the 5 cycle image of 300 seconds primary burn-off. The average diameter from the spec sheet of 14 microns, and then comparing that to the 16.5 microns, we're looking at 2.5 microns total buildup for 5 cycles, which comes out to roughly half a micron per cycle. This is again just an initial estimate. We will be doing further investigations into a more accurate per cycle buildup. Some early cracking, as I mentioned, that 1.4 micron crack. This is another zoomed in image, and you can see that there is some actual buildup happening within that crack. So you can see that it cracked and then has been filled up partially by a subsequent infiltration. Again, when I mentioned that fuzz on the 15 cycle, this one did not have the 300 second initial factory coating burn off. So this was hypothesized to be the reason of this kind of fuzz impurities on the fibers, because in all of the samples that did have the 300 second primary burn off, they did not exhibit this surface roughness. And then another example of the infiltration error, when the cooling system is not functioning properly, you get premature cross-linking as the precursor is deposited onto the sample lattice. And here you can see what almost looks like grain boundaries, but that is actually quote-unquote bubbling due to the polymer cross-linking as it starts to wet out, which then creates a bubble so that it's not actually smoothly brought out. This is a 30 cycle sample. Again, similar to the really good smooth sample a few slides before, this one just had an issue with the cooling system. And then there was some work done by Ben Robles that was reprocessed this year. This work was already presented last year, but there was some reprocessing done. Again, this work looked at taking green fibers, hanging them vertically in a furnace, and then as you heat it up, so they're green, right? They've been cross-linked but not reduced down into a ceramic fiber. So as they're hung, you hold it around you can see in this schematic here, you run it through a vertical furnace, and then you bring that furnace up from 25 degrees C up through 1,000 degrees Celsius at a rate of 15 C per minute. This allows you to look at the strain and elongation and contraction characteristics of the green fibers as they're under different weights. As you can see in part E, this is the loading basket, so the fibers are preloaded, and then as it's heated up, they experience viscous flow, and then as it undergoes pyrolysis, it shrinks down that nominal 30% shrinkage due to pyrolysis as a reduction into ceramic. Here, this was a fairly basic setup, and we'll be doing more research into this. This was just an initial reprocessing of some initial data that was already taken. And here again is some results that are being reshown. You can see from this one graph of the 4 gram loading on these fibers of the true strain versus temperature. It experiences a near linear increase in the strain until a maximum is reached. The strains then decrease and become negative as it contracts due to the reduction into the ceramic. The region of this positive strain, the first section here, the extension, is attributed to the dominance by viscous flow in the polymer. And then, of course, the region of decreasing strain is attributed again to this polymer, to this pyrolysis shrinkage as the polymer is reduced down. Moving back into the current and next endeavors for the Nano-Layer infiltration system, use some Raman spectroscopy to verify that we have indeed had a reduction down into ceramic by looking at those G and D peaks, which are most notable of those silicon carbide. And then we're going to do some thermogravimetric analysis of this pyrolysis cycle, as well as looking for voids in the fabricated CMCs by using 3D nano CT scannings. And then we'll be moving into those next bullet points that I talked about, permeability testing by looking at micro-controlled porosity of samples, and then as well as mechanical testing, and then the supersonic air plasma testing. Thank you very much for your time. Please reach out to me with any questions or comments, and I would like to thank the sponsors, research funding sponsors of the NSF-PIRE, the Polymer-Derived Ceramics, as well as the Schmied Aerospace and the Mechanical Engineering departments at the University of Colorado Boulder, as well as other associates that helped in this research endeavor. Thank you very much, and have a great day.